last but not least, we've got Carl Flottmann with another FPGA kind of based one here, which I thought was really interesting, and we share our supervisor Matthew D'Souza.
Okay. The reason I'm here is because I put in a PSA to the thesis group chat saying, can anyone help me with a problem I'm having? And Max said, come present. So I'm here now. So this will take a little bit of a different turn. Most of you guys are onto the Fintech stuff. I have no idea about that stuff. All of what you guys were just talking about is beyond me. Good luck with the dough. I'm into cyber security. That's what I do. So I'm a 5th year electrical engineering and computer science dual student doing a thesis with D'Souza, and it's on an FPGA-based network intrusion detection system. This is just the seminar slides I have. I haven't seen these since like April when I presented them. So a little bit of progress, of course, has been made since this, but I'll try to speak through stuff that is just like there for the criterion and try touching stuff that I actually progressed on since then. So what am I doing? So I'm focusing on a network intrusion detection system for edge IoT security. So when it comes to cloud computing, we decided that things were getting really slow because we originally had this cloud layer connecting with our edge IoT devices. From your phone, you're connecting straight to the cloud. Everything was really slow because if I wanted to run an intrusion detection system, so this is me trying to detect that there is an attacker on your network, it would have to go through the cloud layer and back. And we want this to sort of act like a forwarding process because we don't want these packets to actually reach you if this has an attack. What are some of these attacks? I don't actually have these in the slides, but some of these attacks might be DDoS is the big one. You can actually see a live map of DDoS attacks currently if you hop on something like Shodan. There is an absolute massive amount of DDoS attacks, like terabits per second, currently happening at the moment. You can see them live, and that's the kind of things that we're trying to detect here. What is my next slide? Some motivation. There's a ton of vulnerabilities in this stuff. So one of the big issues that mine's focusing on resolving is something like the 2016 Mirai botnet. So what happened with that was there was a bunch of IoT devices that were vulnerable to something. Some like Russian hacker guy just said, great, I'm going to just blast this across the network to get a hold of all your devices. He got a hold of billions of devices, I think. Do I have a number here? No, I don't. Yeah, it was in the order of billions, and he launched the largest DDoS attack in history. He took down a few governments, and he took down a few major firms. That's obviously problematic. So that's why this kind of thing that we're doing is required. So a bit of motivation on why am I doing this on an FPGA other than the fact that I'm told I have to. You heard from Max earlier, so all of you are reasonably familiar now with what an FPGA is. Quick recap, it's programmable logic. You are programming the FPGA to basically act as a specified circuit, and it'll run for the function of its duration until you reprogram it, or just switch it off or it blows up. And so that's what makes it fast. You've got hardware accelerated logic. The reason why I want a network intrusion detection system on this is because I want to handle really fast network speeds. So if you've got one of these inside a data center, you're doing things in the order of gigabits per second. Some data centers are now in the order of terabits per second. And so you don't want your network intrusion system to be the bottleneck in it. And so that's why you'd like to write it on something like an FPGA. But as I mentioned earlier, we're doing this on the edge. So we actually need these to be really small. So that's why we got on an FPGA, because that's a small embedded system. This was marking criterion. So was that. I'm doing mine with machine learning. So I found a few papers that actually had substantial resources on these, and I was able to build upon them. I'll touch more on these later. Basically, the rule-based algorithms, you have to do a lot of design in Vivado. Vivado is really big, scary, and it's taking up way too much space on my computer, and I kind of don't want to deal with it. So the machine learning is actually a much better option. For me, I can simulate everything before I actually run on the hardware. We can kind of ignore this, but basically I'm trying to make mine have a really high level of detection performance. I'm trying to make it really small, and I'm trying to make it really fast. To give you an idea of kind of size, we only have spaces in the order of kilobytes of FPGAs. And many of you may have dealt with our models before. They're generally in the order of megabytes to gigabytes. So getting something down to something small enough on an FPGA is actually quite challenging. Max gave you the example earlier of what Vitis AI and all the really complicated compilation stuff does. Mine's a little different, but they all focus on making really small, fast-running models. So what am I doing? Mine is using a weightless neural network. So these are specialized types of neural network. A usual neural network will have something that runs with multiplications. So you generally have nodes that are performing multiplication operations. Now these are really expensive pieces of logic in an FPGA. They're generally actually specialized logic chips, I suppose, but the sectioned out part of an FPGA, you can only use a certain amount of them. I think, like my board has something like 48. There's not a lot of multiplication operations that you can perform. So they're really problematic. So we started looking at these weightless neural networks. So instead of multiplication operations, you do these table lookups. So you have a RAM node, like what I'm showing here. It's just something you have n inputs, and then you have 2 to the n entries inside, and that gives you a result. And what you do is you combine a bunch of those and sum them together using a pop count method, and then that is one of your discriminators. You combine a bunch of these, you do some really funky routing to map everything to the individual RAM nodes in these discriminators, and then you're going to get a result. The problem with these, many of you other guys may have already noticed, is you've got 2 to the n entries in your RAM block. That makes things increase in size very, very quickly, exponentially. That's all the things I just said. But it was really accurate was the cool thing. This one was only 192 bytes in total size. Now that's actually incredibly small. It's the smallest model that I could find, and I reviewed 100 papers. So that is quite a small FPGA model. The biggest issue with this one, and it was fast, order of gigabits per second. But the biggest issue with this one were the input features. So the input dataset this was trained on is called UNSW-ND15. That's actually trained our mates down at UNSW. They offer that on a SharePoint for some reason. That actually gets flagged as malware when you access it. Anyway, that has what are called connections over time features. So things like the total duration of a connection may be in a feature. And that's something that builds up over time as your network functions. Now, that's not going to be particularly useful if I do want something to run at gigabits per second in real time, because I have to wait until the total connection of my network is done before I actually tell you whether you've been attacked. And by then, I've already installed the crypto miner on your computer, so anyways. Yeah. So what did I do? I found another open source repo. This one used real-time feature extraction to do this. So they actually use the raw bytes in your network payload to perform the detections as opposed to all the funky features I've shown you earlier. But the problem with these is actually ordering them in a good way. So the previous paper that I don't have up here because it was kind of useless, but they just started shoving bytes into the weightless neural network, and they got something in the order of 30 to 40% detection rate. The SOC engineers who would be reviewing that would kill themselves within a day if they had to deal with that level of false positive rate. So that's not ideal. So what they did is they started sorting things based on the flow identifier. So that's made up of your source, destination, IP, and port, and the protocol. And that just typical standard headers that you require in every TCP or UDP packets or other protocols as well. So you use these, you sort them into buckets, and a bucket is going to contain some amount of packets that is fixed, and it's going to take a fixed amount of bytes as well, and then you're going to get your funky 2D input that you can now use as input to your AI model. 2D inputs is things where our AI people will know we are happy with these, and we can use these as input to our AI model. These guys, though, they use something similar to what Max is doing, a convolutional neural network architecture, and they quantized it down using something similar to Vitis AI.
I think that's the TensorFlow one.
Is this the TensorFlow?
I think Fin is the TensorFlow, or maybe the older version of the one I'm using.
Okay.
So it's same workflow.
Yeah, kind of same workflow. You quantize it, go through a really bunch of annoying compilation stages, and that pops your model down onto your FPGA board. Really high level of test accuracy, but it basically took up the whole FPGA. We want it to be much smaller because the FPGA is going to be our edge IoT node, so it also needs to do a bunch of other things like routing, actually storing like data that you're getting from all your other sensors. So it takes up almost all of your resources that's not particularly useful. So my proposed solution is I'm going to smush them together because I've got two open source resource code bases that I can use, and I've got two different ideas that I can smush together to achieve the three highlighted in blue design criteria I was showing earlier. So what does this look like? I don't have a Vivado example to show you because I've got to install it on an app. But basically it looks like this. I'm going to take incoming traffic, I'm going to shove it through the PS. For those unfamiliar with the FPGA stuff again, the PS is the processing system. So if any of you have done any of the embedded system classes dealing like 3010, 2010, what you guys are programming on is PS, it's a processing system. You program it like an embedded system in C, it runs on the CPU. Now the PL, as well as discussing earlier, that's our programmable logic. We write that in a hardware scripted language. It looks the HDL system Verilog, and it's a very different way that I can really show it earlier. But the thing that they share is the DRAM, and the DRAM is what we're going to use to shove our packets into the DRAM. I'll do a bunch of fancy things, active DNA is can't get to work right now, but we'll use that to extract it, shove it through our bucket sorter into my model, and then pipe it back out. Tool selection, honestly, didn't have a lot of choice. I have to use Vivado because that's the only thing my board is compatible with. I didn't want to buy an FPGA. I eventually got given one, and it only works on Vivado. So that's why I'm using Vivado. But it also has all the cores that I need. So the DMA is something I do not want to write myself, and so I can just pop that in. Vivado, for a lot of FPGA things, you can actually just pop things in like blocks / connect the dots. There's also a bunch of connection configuration it can run for you. So a lot of that is automated and that you don't have to worry about it. Also, I thought that's a different issue. And then the other thing I'm using processing system is Zephyr. So Max discussed earlier, he was using Pedalix. Pedalix is basically an embedded system designed Linux distribution. Zephyr is like a slightly more what we call bare metal version. So Xilinx, who procure the boards, they do actually provide their own API, but it's particularly complicated and you have to custom write all the stuff that Max is doing. Zephyr is kind of like an intermediary one. The only problem is it is open source, so no one documents anything. And that's why I'm liaising with a random guy in Germany right now about my problem. But the deal is Zephyr is going to make it slightly faster, it's slightly more bare metal. So the actual AI model training. So we just try and test optimize all that business in PyTorch. I had to email the guys in Frankfurt saying, please give me more space. You only give me 5 gigs, I need 50 gigs, please, please, please. They eventually gave it to me. And once I've got the model in PyTorch, though, the trick is getting on the FPGA, as Max has so happily discovered. What I'm doing, and what was kind of already done in the code base I've been using, is we use these things called macro templates. So once I train it, it's actually going to give you a bunch of parameters. Macro templates basically lets you write any kind of file, template it out. So in my case, system Verilog, which is a code file. But you write some of the parts in Python so that when you render it, it runs that Python code and then it spits your file back out. And so that's what these do is they render the configuration based on what my AI model actually trains, and it spits it out to VCS synopsis, and that like does all the verification, make sure it actually works. I don't want to pay for it, so I instead ported that over to Verilog, which is just a free open source and slightly less annoying version of that. And the rest of that is just like semantic stuff. Yeah. Since then, I don't know if slides work because I haven't looked at these. Since then, we have got it working. I've got it working in PyTorch, and I've got it working in System Verilog as well. I'm getting a 99% detection rate, it's fantastic.
theoretically 400,000 samples per second, which is pretty fast, and then it's only about 6 kilobytes. So now I've got to keep liaising with the friend guy in Germany to get this is working. That's all I have.
Just a quick question. My question was, would you just be able to like elaborate a little bit on what particularly you're liaising with, like what you're trying to solve there, I guess, with that guy? Because I thought that was kind of interesting or funny.
Yeah. So what I was showing you before, is this? No, that's something else.
It'll be a different slides.
I can't bother to do that.
Yeah, it's all good.
What I was showing you before, I was discussing the DRAM and the AXI DMA. So DMA, for those of you who haven't seen 3010 yet, get keen. Direct memory access. So instead of accessing all the memory stuff, which you usually do through the CPU, go through a bunch of really annoying little things, and then eventually go out to memory. DMA is basically go straight to the memory, pull it out, and pull it into my system. So much faster. You have this actual DMA controller that handles it for you, but that's the only intermediary. To liaise with AXI DMA in Zephyr, you need like a driver and to pop something in what's called the device tree. So it means you just state, I have AXI DMA and it's located here. And then the guy in Germany wrote a bunch of really complicated, long 2,000 line C files to actually interact with that thing. And what I'm talking to him about now is every time I use it, it tells me that it can't access the memory location and that it's not there. And that's the current issue at the moment. Vivado is very fancy. You can do a lot of different things with it. So you can, if any of you have done any embedded systems, you may have used logic analyzers before. In Vivado, you can actually use an integrated one, so it turns your computer into a logic analyzer, and you can actually see all that business if you plug it in, like Max had with USB, and see all the signals. So I'm changing on that.
Question for you and Max, like these monoliths getting compressed by like orders of magnitude, what kind of performance hit do you see from them?
So for mine, and something that I've actually found in my thesis, so Max was discussing earlier with the pruning. So generally if you want to quantize a model, like Max mentioned, you're kind of losing accuracy already when you try to quantize it. Because you're making this smaller, it's going only fixed point integers, you don't just have the infinite integer size for yourself to deal with, right? And the pruning, what that does is supposed to account for the loss in accuracy that happens when you do the quantization. So usually, like what mine does is it will find all the filters, all the discriminators that just aren't firing, so like they're not doing anything, or they're just really lazy, or barely firing, or they're always producing like the same result, they're always producing maybe zeros or ones, and it will actually get rid of them or rewire and remap the inputs to them, and then it will retrain the model with that new rewiring and mapping to see if that increases accuracy. That's what mine does. The interesting thing with mine, so most models work that way, the interesting thing with mine is it doesn't require that. All the input mapping and rewiring already fires enough, and that's because I'm using the raw bytes and bits as I was describing with the input features earlier. Traditionally that's how you do it, is you rewire all the inputs so you can squish it down further. And you can generally configure like the percentage of pruning and like squishing that you want to do. There is definitely a loss of accuracy, and it's like a trade-off that you have to kind of like